Okay, so we start the second session of the afternoon. Markus this time is going to give a lecture on the neutrino emission from AGNs. Okay, so please.
All right, thank you. All right, so I know you've been sitting through 4.5 hours of lectures already. I promise you this one will probably be a little bit shorter than 1.5 hours. So it's neutrino emission from AGN. Specifically, because you probably know the biggest results that we have from neutrinos come from the IceCube experiment on the South Pole. So it's built right at the Amundsen-Scott station on Antarctica, right at the South Pole, being 86 strings of digital optical modules that measure Cherenkov light from secondary particles from neutrino interactions deep in the ice of the Antarctic, 1,400 meters below the ground and going down another 1,000 meters into the ice. Neutrino detections work exactly in this way, that neutrinos somewhere in the matter of the ice interact. Neutrinos themselves, of course, are not directly detected. They have to be detected by interacting with matter, ejecting, scattering normal material, producing electrons or muons, and it's the secondary particles, these muons or electrons, that are essentially then detected through Cherenkov light of secondary particles in the showers that are produced by their interactions. In this case, we're talking about high-energy neutrinos. Of course, there are neutrino detectors at lower energies that measure things like solar neutrinos of a few MeV energies. With IceCube, with these Cherenkov detectors, we're detecting neutrinos in the TeV to PeV range. IceCube primarily actually sees neutrinos coming all the way through the ice, so through the Earth, at least up to about a PeV. You probably know neutrinos are extremely weakly interacting particles. They essentially penetrate everything without interacting at all. In fact, from solar neutrinos, the body is penetrated by solar neutrinos all the time. There's a nice anecdote of a colleague of mine at the University of Dortmund who had a sign on his office door saying, upon entering this office, your body will be penetrated by 100 trillion neutrinos every second, with the consequence that ever since the janitors refused to enter his office. Maybe not the desired effect. So be careful with the jokes you're making about neutrinos. But anyway, this is why IceCube is primarily seeing neutrinos coming from the other half of the sky, so from the northern hemisphere, penetrating all the way through Earth, because no other particle can come from that direction. So what kind of neutrinos we're detecting with IceCube? We can distinguish by the shape of the tracks or the signatures that the interactions leave in the ice. If we're dealing with a muon neutrino that produces in a charged current interaction with the matter a muon that has high momentum, high mass, produces a relatively long, nice, straight track that points back to the direction of the source, to within about 0.4 degrees. So it gives us a nice localization. One can do neutrino astronomy with that. Downside is that quite often these tracks start outside the detector or they end outside the detector, so not all of the energy released is actually deposited in the detector, so the energy resolution is often quite poor. The opposite is true for electron neutrinos that often produce these shower-like events. So electrons depositing their energy very localized in an almost isotropic way. All the energy is contained in the detector. One can measure the energy very well, but one has a very poor spatial localization up to 8 degrees, so it's almost impossible to really pinpoint where those neutrinos are actually coming from. And then there are very rare double bang events from tau neutrinos that produce a tau meson that produces one localized shower, and then a couple meters away, this tau muon, this tau lepton decays, produces another shower, so it gives you essentially two banks related to the same events. But those, as I said, are relatively rare, and they're not really used in neutrino astronomy. So one of the biggest breakthroughs, I think, in the last, that's more than a decade now, is that IceCube published the detection of actual astrophysical neutrinos. Most of what IceCube sees are actually neutrinos that are produced when cosmic rays interact with the atmosphere. They produce muons and also neutrinos, and that can essentially not directly be distinguished from any astrophysical sources. The thing is that this atmospheric muon background essentially reflects the very steep cosmic ray spectrum of about e to the minus 3 or so. Whereas since 2013, we know that there is an additional component likely associated with astrophysical sources that has a much harder spectrum, about e to the minus 2. And they intersect at about 100 TeV or so. So if there is a neutrino event seen at energies significantly above 100 TeV, there's a high probability that it's not part of this atmospheric neutrino background, but it's actually related to an astrophysical source. Actually, one of the newest news that I won't say much more about is that IceCube has just published a paper saying that this is actually not a straight power law going all the way down to sub-TeV energies, but there's actually a turnover here. So there is some spectral feature, but of course, below that big dominating background of atmospheric neutrinos, it's very hard to really quantify in any more detail. All right, so the question is, where do these neutrinos come from, these astrophysical neutrinos? There's a couple of hotspots here where there's enhanced probability of excess neutrinos. Again, most of the neutrino events, of course, are in this lower energy part where essentially all of the neutrinos are atmospheric neutrinos. But there are hotspots where there's more than expected from atmospheric background. Again, you can't pinpoint for any individual neutrino whether it's atmospheric or astrophysical. We can just say there's some excess there. Some of those neutrinos might be of astrophysical origin. And many of the hotspots that are identified here are actually associated with blazars. There's more and more compelling evidence that blazars make a substantial contribution to this atmospheric, to this astrophysical neutrino signal that is seen. Even though there are statistical arguments based also on the gamma ray background that not all of the astrophysical neutrino signal can be from blazars. So we know blazars most likely make some part of that neutrino signal, but not all of it. There's also an association specifically with blazars, with radio-loud blazars that are very strongly core-dominated. So the group by Yuri Kovalev and Sasha Plavin has put out a couple of papers making this correlation more and more solid. So we know that there is a significant contribution from these core-dominated radio-loud blazars. So you remember this one from the last lecture. We talked about hadronic processes, and we said if we want to make neutrinos with blazars, we need ultra-relativistic protons that produce neutrinos by interacting with radiation, in this case, and muon, a pion and muon decay gives you 3 neutrinos per charged pion decay. So in general, any astrophysical source, one can produce neutrinos by either slamming relativistic protons into other protons that can either produce just a pi 0 and leave 2 protons, or you can have a neutron coming out, then you would have the charge, the positive charge in a pion. And at high energies, these interactions can even produce more particles. So not just one neutron, one pion, you can have multiple pairs of pi plus, pi minus in addition to that. For interactions with photons, so photopion production, protons slamming into gamma rays or lower energy radiation, can either give out the proton and make a pi 0, or you can transfer the charge to a pi plus. And then the pi 0 decays to 2 gamma rays. the pi plus or minus decay into muons and neutrinos, and the muons again decaying into electrons, positrons, and more neutrinos. So again, for each charged pion decay, you get out 3 neutrinos in the end. You can see that this happens very quickly, essentially instantly. So in most treatments, one assumes that actually these decays happen immediately, and one doesn't care much about what's happening to these intermediate products. All right. So there's 2 ways of making neutrinos. We have to figure out which one of these channels is most likely dominant in blazars. Which one is dominant? Well, it depends on the relative length of the interaction timescales. So the timescale for a proton to hit another proton, or the timescale for a proton to hit a target photon. Those are just inversely proportional to the density of the target fields. We said in the previous slides, the cross-sections are really of the same order here. So really what matters for the interaction rates is the density of targets to interact with. So let's figure that out. The density of photons that we expect, we can kind of relate to the density of synchrotron photons. That would be the primary targets, the densest radiation field that's there in terms of number density, that we can relate to an observed synchrotron luminosity. We know from Doppler boosting it's actually enhanced by 4 Doppler factors, so the intrinsic density is lower by 4 Doppler factors. And then we just divide by the photon energy and the converting luminosity to densities. And we get something of the order 10 to the 18 photons per cubic centimeters for a size of, say, 10 to the 16 centimeters synchrotron luminosity, typical 10 to the 44 ergs per second, and a Doppler factor of 10 as characteristic values. See, the exact values don't really matter for the arguments that I'm making here, because if you compare that to the typical number density of protons in a blazar jet, say the total luminosity in the jet is carried by the kinetic energy of protons, well, then we take that jet energy, divide by 2 Lorentz factors, the proton mass, and then again converting into number densities. You get something that's some 12 orders of magnitude less. So the exact numbers of these values we choose for the jet luminosity and Lorentz factor don't really matter here. So all in all, that means that typically proton-photon interactions are some 10 to the 14 times more efficient than proton-proton interactions. So that means, in effect, we can forget proton-proton interactions in blazars. We only need to worry about photopion processes. So in photon-pion processes, as we said, produce either neutral or charged pions, whatever is coming out, in particular in neutrinos. Neutrinos are essentially massless. They're Doppler boosted into our observing frame in essentially the same way as photons are. So we get the same kind of Doppler boosting constraints as we had for gamma rays. A bit more about the physics and the energetics. If we look at the cross-section for photopion productions to occur, this is the energy of the target photon in the proton rest frame, and that's the cross-section. You see that that is very strongly dominated by a resonance called the delta plus resonance, in which the photon essentially excites the proton into a delta plus resonance, and the delta plus particle immediately decays into either neutron and pi plus or proton and pi zero. That is just a little bit above the interaction threshold here at 1232 MeV in the proton rest frame. This gets even more extreme if we consider that target photon fields in astrophysical environments are typically power laws, relatively steep power laws. That means not only is the cross-section here much higher, but also going to higher and higher energies, you have less and less photons to interact with, right? Because you need higher energy photons to interact at higher center of momentum energies or proton rest frame energies. So this is essentially the interaction probability for interacting with photons of spectral, with target photon fields, with spectral indices of typical values like 2 to 3 or so. And you see that this is really completely dominated here at this low energy end. So that means for first order approximations, we can essentially say that pretty much everything happens right there at the delta resonance. For detailed modeling, of course, you want to do a bit better than that, but just for basic energetics considerations, you can say everything happens at the delta resonance. All right, most likely, most of you who have had any courses in special relativity have calculated the photopion production threshold just from energy and momentum conservation, meaning to interact with, say, target photons of order an electron volt, that means optical photons. You need protons with something of the order 10 to the 17 electron volts. You've heard something about cosmic rays already, I believe. So this is definitely beyond the knee of the cosmic ray spectrum. It's getting close to ultra-high energy cosmic ray regime, what we need for this to happen. So at the delta resonance, S here is the center of momentum energy squared of the interaction, given by the proton and the target photon energy times this relative velocity term. At the resonance, this just equals the energy of the delta resonance squared. Now, the proton energy we can constrain from the kinematics. About every neutrino takes about 5% of the energy of the proton if we have a reaction of proton plus photon to neutron plus pi 0 and then decaying on to neutrinos. The 3 neutrinos, each one of them take 5% of the neutrino energy, of the proton energy. That means the proton energy is just 20 times the neutrino energy that we're looking at. So now, considering that we have neutrinos Doppler boosted by a Doppler factor of about 10 or so, so if we're looking at a 100 TeV neutrino, above which IceCube confidently can detect astrophysical neutrinos, that's about 10 TeV in the emission region rest frame. Then we need protons with 20 times that energy. So we need some 200 TeV to PeV protons in the rest frame in order for this interaction to happen. And then, well, we can invert this to find the target photon energy. We need target photons at KeV, that means X-ray energies. And the higher energy neutrinos we're looking at, this goes inversely proportional to the neutrino energy. Well, the logic being we constrain proton energy times target photon energy. Proton energy is 20 times the neutrino energy. Higher neutrino energy means we need lower energy target photons and vice versa. Right? So we need X-ray photons to make 100 TeV neutrinos in blazar jets. So let's consider that maybe these are target photons that are, say, synchrotron photons produced in the same emission region. Then these synchrotron photons also Doppler boosted towards us, right? So we see them Doppler boosted as hard X-rays. So in this way, but hard X-ray flux in many of the sources that we see or suspect to be neutrino sources, the hard X-ray flux is relatively low. We see them Doppler boosted in energy, but also in intensity, right? So any given neutrino flux we want to observe requires a certain density of target photons, but then the X-rays that we see directly, if they don't interact with protons, are pretty bright X-ray component that's often hard to reconcile with the blazar SED. It gets much better if the target photons are stationary in the AGN frame and not boosted towards us, but the emission region is moving through that target photon field. So the emission region actually already sees it Doppler boosted into its own frame. So we see it at the same energy actually we needed the 1.6 keV in the rest frame of the emission region. That means in the AGN frame, and thereby in our frame, it's actually even lower. It's somewhere in the soft X-rays or ultraviolet, where quite often we have very weak constraints. And we don't see it Doppler boosted. We don't see a bright flux in that range, but the emission region sees it enhanced. So that is much more favorable actually for all the energetics constraints. So all these models that we'll discuss work much better if we have an external radiation field that the jet is moving through and sees it enhanced, and we don't see so much of it. All right, there's one fundamental problem for making photopion production and neutrinos and producing gamma rays at the same time. So here's the cross-section, that's the P-gamma cross-section. Here's the gamma-gamma photon-photon absorption cross-section. The basic problem we encounter is that if we have a dense target photon fields that protons can slam into and make neutrinos, that same photon field can also absorb gamma rays to produce electron-positron pairs, so the gamma rays can't get out. So this is the optical depth for protons to interact with the photon field. This is the optical depth for photons essentially to get out of the region. And this shows that for typical parameters, the gamma-gamma opacity is 3 times higher than the proton interaction probability. That means for photons that have just the right energy to interact here near the peak of this gamma-gamma cross-section of about 10 times 10 to the minus 5 of the neutrino energy, that's actually exactly the Fermi to Cherenkov telescope array energy range, the gamma rays that we see from blazars. Those are very likely absorbed if we have a target photon field with which we can make the neutrinos. So it's very difficult to have the same region that makes the neutrinos, but at the same time allows the gamma rays to get out. So most likely is that if we see gamma rays from a blazar, they're not made in that same emission region, because it's lightly optically thick to gamma rays. So we don't necessarily expect a correlation between neutrino activity and gamma ray activity. And most searches for counterparts are actually relying on correlations between gamma ray activity and neutrino activity, but it's not necessarily expected. So the shift is more and more now to look for what's coming out of these gamma rays interacting, where they produce pairs, more gamma rays, more pairs, more absorption, until it becomes optically thin. And you get these cascades. They extend way into the X-ray and ultraviolet. So more likely is that this neutrino production activity will be reflected by cascades down to X-rays and ultraviolet. So you'd much more expect the neutrinos to correlate with X-rays than gamma rays. There's one other argument here for modeling neutrino emission from blazars. Originally, a lot of people were just trying to model to get at least one neutrino detection probability for any neutrino flare that people have seen. But the problem is, there's a lot of blazars out there, all of them probably doing similar things. The fact that maybe we see every once in a while a neutrino from one of them. At the same time, there's maybe of order of 100 of other blazars that probably do the same thing, possibly have the same neutrino flux. So if you see only one of them with one neutrino and the others not at all, that means the actual flux is probably so that you only expect like 1% of the neutrino from. So that looking at 100, you see one. So that means the flux that you really need to produce with neutrino models is probably much less than a probability of 1 to actually detect a neutrino, because we see so many other blazars from which we don't see neutrinos. All right, maybe a little bit to the formalism. How does one, in practice, model neutrino production? One that's very often used is a method by Kellner and Aharonian in 2008 that essentially used Monte Carlo simulations of these interactions, looked at the spectra as they come out, and parameterized the outcoming photon and neutrino spectra in their end state after all decays have happened. It's essentially just some physics considerations, but otherwise just a phenomenological model fit to the spectra that ultimately come out for a given proton and photon energy. That's essentially this phi function here, and then you just integrate over the photon and proton distributions to get the final output spectra. This is very quick, easy to do. The only drawback is that this neglects anything that the pions and the muons might do before they decay. So this integrates out immediately to the final decay products. So if the pion or the muon actually produce significant synchrotron radiation and cool before they decay, then one can't apply this. And that effectively restricts the range of maximum proton Lorentz factor and magnetic field to this range. Many models are within that range, but quite often, if the magnetic field, say, is higher, then the protons, the pions and muons have too high energy, they actually radiate significantly before they decay, and then the results become wrong. Alternatively, and more generally applicable, is then to carry through all the secondary particles, the pions and the muons, and this, so my former PhD student Chris Dills has developed a code like that. So there are similar templates of these decay products, the spectra of these decay products by Hümer et al. From 2010. So there you can have these coupled differential equations where for every particle species, not only pions, but also muons, protons, electrons, positrons, and so on, you see how the spectra change over time through acceleration processes, radiative processes, that's essentially synchrotron. You have production, the pion production, and of course, if pions decay, you have the same as a source term for the muon production, and if muons decay, then the muon decay gives us a source term for electron-positron production. Particles may escape, and they decay, and again, the decay then gives essentially the source for the next set of particles. So one has to iteratively integrate this to get a time evolution here. That's the more detailed way of doing this. All right. A few, actually just two special cases. Many of you may have heard of this very famous, really first and so far I think most significant association between a neutrino event and a flaring blazar. So the IceCube event on September 22nd, 2017. That's how the IceCube events are named, just by their dates. So this was a nice straight muon track event. So you see the image of it here of about 290 TeV. So that's about a 50% probability that that is actually astrophysical. And again, that's the caveat. That also means it's a 50% probability that it might be background. But it was coincident with until then pretty unknown blazar TXS 0506 plus 056 that was in a 4-week-long gamma ray flaring state. And the association, again, it's just 3 sigma, but the best that we have so far. I see the long-term light curve here. In particular, that second panel here is the Fermi gamma ray light curve. The blazar, since the beginning of the Fermi mission, has been very quiet and suddenly flared up here, and that coincides with the detection of this IceCube neutrino. And this is actually why this is considered a fairly reliable association between the blazar and the neutrino. And also MAGIC started observing after this alert and also detected it in very high energy gamma rays. Then there's archival data of lower energy neutrino events, most of them, of course, atmospheric background, but there was evidence of about 13 excess neutrinos from that same direction likely from that same blazar in 2014-15. And remarkably, as opposed to the 2017 event, no gamma ray activity whatsoever. So the gamma rays are just plain flat here, but there was this neutrino excess that apparently has nothing to do with any gamma ray activity, which again is what I said we might expect because of this opacity constraint. So most likely the gamma rays are actually made, at least by different processes, maybe in a different region than the neutrinos. Then, of course, there was about 100 papers by theorists trying to model this. And the general picture that emerged was that, as we had seen from these energetics constraints, we need X-rays to make neutrinos in the 100 TeV regime. Models that try to use the co-moving synchrotron flux here produce neutrinos that actually have way too high energies. So it's very difficult to reconcile that with the energy of the ice cube neutrino measured. Then there's models that tried to produce the gamma rays really dominated by hadronic processes, by pion production, pion decay, and cascading. First of all, they run into exactly this opacity problem that we talked about. So the gamma rays cut off too early. And more severely, the cascades extend with a smooth spectrum here way into the X-rays and way overshoot the measured X-ray spectra here. So that's, again, a fundamental problem. So that's why the convergence over the following year or so was that it's really not plausible to make the entire SED with hadronic processes. So most of the models from here on then converged on something where the electromagnetic output is actually dominated by leptonic processes, by synchrotron and Compton scattering, whereas there's a subdominant contribution only from the hadronic processes that make a neutrino flux that is actually less than corresponding to a probability of detecting one neutrino. But there's the Eddington bias. You don't really need to predict the probability of one to detect a neutrino, or the probability to have one neutrino over a certain time, because there's so many other blazars that we don't see. Okay. Interesting new development is that there was actually another event in 2021 by neutrino observatory in Lake Baikal in Russia, Baikal GVD, that detected another neutrino from a source consistent with TXS 0506. But whether that is really an association or not, have to take with a large grain of salt. You see, this is the source location of the ice cube event here. This is the Baikal GVD, 90%, and you see that there's a much larger error region. So there's a lot of other sources in that field that could also be responsible for it. So one would have to be very careful in interpreting this really as another neutrino from the same source. Another specific case that I'll just talk about is this one. Parks 0735 +17, coincident with a neutrino event by IceCube in December 2021. The remarkable thing here is that there was not only that one IceCube neutrino, but within about a week of this event, Baikal GVD also detected a TeV neutrino 4 hours later. There's an underground experiment also in Russia that detected a GeV neutrino also around that same time. And there was actually evidence for a KM3net. I haven't talked much about KM3net. So KM3net is a neutrino detector currently under development, under construction in the Mediterranean Sea. Of about 18 TeV, that was also essentially coincident with this. So this could be the first blazar where we actually have 2, 3, or maybe even 4 neutrinos by different experiments detected from essentially the same direction. So this would really be a game changer. You see here the multi-wavelength activity. This again was coincident with gamma ray activity of this blazar, which, if it's not hadronically initiated, maybe that is still plausible. And you see all the different alerts here from, this is Baksan, IceCube, Baikal and KM3net, so all within about a week during this time of very high multi-wavelength activity. And the modeling, I'm not going to go into very much detail. Like in TXS-0506, the best solution found was to have the SED, the electromagnetic SED, actually dominated by leptonic processes, synchrotron and Compton scattering, and hadronic processes, only making a subdominant contribution. Maybe this is a good time to take a minute or two of break and ask if there's any questions or comments.
In some slides before, you put a proportion between the pion production into charged pions and neutral pions of 2 to 1. Is this like a general proportional? What's the energy range for this?
Yeah, I think that's applicable generally. That's the characteristic of the delta plus decay.
Okay,
Yeah.
thank you.
Questions? Yes.
Did the first neutrino observation from IceCube from that blazer that had a signal in photon 2, did they use that to constrain the target density for photon prime production?
Yes, of course. There are a lot of papers doing exactly that, and yeah, I can point you to some references if you like.
More questions? Okay, guess not.
Okay, very good. Then now we've had all this talk about neutrino production from blazars, but the truth is, we look at the northern hemisphere map of excesses of lower energy neutrinos from IceCube. The brightest hotspot in that, see there's two hotspots here, the TXS-0506 that we talked about. This was one earlier alert of a possible coincidence that also a hotspot. But the brightest hotspot is actually this thing here. That's NGC 1068. That's not a blazar. It has only a very weak radio jet, it's really radio quiet. It's a composite Seyfert galaxy and starburst galaxy. So here it's unlikely that these processes we talked about for jet neutrino production with photopion production are really playing an important role here. So most likely this makes neutrinos in very different ways. So in Seyfert and especially in starburst environments, because we have much denser target proton densities, gas densities. So here it's much more likely that actually the neutrino emission is really contributed by proton-proton interactions. So most likely, so not from the jets, but either starburst. Starburst means you have a lot of star formation, young stars, massive stars form. They die early, produce supernovae, they produce cosmic rays. Cosmic rays can slam into protons in the environment, make gamma rays and neutrinos. Or you have, well, AGN. It is an AGN, so it has a strong accretion disk. Accretion disks drive not only jets, but winds off that can produce shocks, accelerate particles, and those can slam into the environment. So here it's much more likely that there's actually interactions of cosmic rays with gas, with other protons. If we compare, so this is an excess based on a significant number of neutrinos. It's not just one neutrino event. So here one can actually calculate a spectrum of this excess over the atmospheric background. That is this blue curve here. And this is the electromagnetic output here, bright host galaxy contribution here. But then there is a faint radio signal here from these faint radio jets. And this is detected in Fermi-Lat. These are Fermi-Lat points. And Cherenkov telescopes have looked at it, not found anything at 100 GeV to TeV energies. But it stands out that the neutrino flux is actually about an order of magnitude higher than the Fermi-Lat gamma ray flux. So here, the output at high energies is really dominated by neutrinos rather than gamma rays. So again, there's a lot of different ideas, a lot of different models that I really cannot do any reasonable justice to go into detail into all of these possibilities that have been suggested here. Maybe a really comprehensive review of different models is this recent paper by Das et al. 2024. You have the reference here. So, but most likely, the neutrino production has something to do with outflows and winds from this accretion disk that slams into this accreting material, maybe broadline region material, interstellar medium, with proton-proton interactions likely dominating the neutrino emission, or alternatively, it can just be the starburst activity. That means supernovae accelerating cosmic rays that make PeV protons that can produce high-energy neutrinos. Let's talk a little bit about the physics and constraints on proton-proton interactions. As we'll see, these are actually much more complicated, much more involved, not as relatively easily tractable as the photopion production, where the delta resonance dominates everything. First point is, with 2 protons, you already have quite a large rest mass energy that is there. You don't need a lot of extra energy to produce the relatively low energy, low mass pions. In fact, if you have a proton at rest and you slam another proton into it, the proton needs to be really only mildly relativistic in order to start producing at least 1 pion, say 1.2 GeV, Lorentz factor of 1.3 or so. But that, of course, means that the pion is almost at rest at that point. So pion of 32 MeV, not anywhere near the TeV range that we want to look at. So again, we need the additional energy to make higher energy pions, and thereby higher energy muons and neutrinos out of that relativistic protons. So again, we need really the ultra relativistic protons. Obviously, you need to have at least the energy of the neutrino you want to produce in order to make 100 TeV to PeV neutrinos. Another complication is, at the cross-section, there is not a really significant contribution from single pion production. Most of what we get here at high interaction energies, so this is energy, the square root of S, the center of momentum energy of the interaction. At the high energies here, it's very strongly dominated by not just making 1 pion, but the higher the energy is, the more pions you make. So that means you're distributing the energy that you have available in the proton to more and more particles, so you get less and less efficient in really making high energy neutrinos. Rather than making higher energy secondaries, you just make more of them. So there's a lot of, in order to do the physics really correctly for detailed modeling, one would have to do some Monte Carlo simulations of these interactions. Here's a couple of references to codes that are available to do that. Let's talk a little bit about some more quasi-analytical approximations. Again, by Kellner et al. 2006, came up with parameterizations of finding the ultimate decay products. So it's here for as a function of the energy of produced particles, say the pions, that comes out. And you see, the higher the energy of the proton is that slams into another proton, to the lower the fraction of proton energy that is transferred to the pions. So the higher we go, the flatter this curve becomes. And so, say if you have a PeV proton slamming in, most of the secondaries really only have energies here of 1% or much less than 1% of that energy. So that signifies that problem, having higher energy available, you don't make so much higher energy secondaries, you rather just make more of them to distribute the energy onto more particles. And that makes a fundamental problem in producing these very high energy neutrinos with proton-proton interactions. So this really illustrates the exact same thing here. So don't need to do much more. So that points us to this Kellner et al. Paper. Here's the exact reference that gives you the ultimate decay product spectra. So if you have a proton and a relativistic proton and a target proton slamming into each other, it gives you, as a function of proton energy, the energy spectrum of the final decay products that one can use to model the secondary outputs, the electromagnetic and neutrino outputs. And again, there's a huge body of literature out there on different models. Of course, NGC 1068 being the brightest hotspot, the most significant neutrino source out there as an AGN. I cannot possibly do justice all of that. I'm just showing one example here of a paper by Kota Murasa in 2022 that explored a couple of different scenarios to try to model the ice cube spectrum. You see the different ideas here with different ways that cascades from pion decay are supported either via synchrotron or Compton scattering. One can get not too great a representation of the Fermi spectrum here. So all of this is clearly still suboptimal. But so there's a lot of literature out there that I cannot possibly summarize altogether. But this just gives some example of what a typical modeling of neutrino and the electromagnetic output looks like. It's all consistently not predicting any VHE gamma ray emission. So I think MAGIC, I'm not sure if Veritas has looked at the source, but nothing has been detected there, so this is consistent. And that's already all I have. I promised you I'd be short.
What about the latest Game3Net event, the very ultra high energy neutrino? Do you have any comments?
Only comment is that it's unlikely to be AGN related. Right? So yeah, there was, in case you haven't heard it, there was this ultra high energy neutrino event by KM3Net, a 220 PeV neutrino hitting the detector from almost horizontally. There are a few blazars in the error region of that, but none of them really showing any significant signs of activity that would really hint to them being the source of such a high energy neutrino. And physically, it's very difficult to produce that in an AGN context anyway. There have been ideas of galactic sources, which is also very unlikely because there really aren't any convincing possible counterparts there. I think the most likely probability is that it's cosmogenic, so meaning that we have ultra-high energy cosmic rays anywhere in the universe interacting with cosmic microwave background, exactly what gives the cosmic ray spectrum this GZK cutoff. That process obviously produces pions and subsequently neutrinos that could be of similar energy. That fits reasonably well. The only problem with that is that, of course, instruments like IceCube have looked at the neutrino sky for more than a decade and not seen a similar event. And that is a little bit of a tension. I think they can tweak it so that it's just so still okay, but that is becoming a bit of a problem. That's the only problem, but I think it's the best explanation that I think is out there. I don't think any other explanation is really plausible.
Yes, more questions? Such a rich topic in lots of kind of physics. Any more questions?
Everybody's tired.
Okay.
I can see why.
Well, anyway, so I want to thank our lecturer for these two wonderful, interesting lectures on very important topics. So let's give him a hand. So what's next?